The oscillogram is probably the single most important tool for analyzing faults on the power system. Just what can we tell from this collection of wiggles on a piece of paper or on a computer screen?
Well, very quickly, we can deduce what type of fault occurred. Phase to ground, phase to phase, and so on. What phases were involved, and whether or not the breakers and relays operated correctly.
Now, just how much system data do we need in order to make a proper diagnosis of system faults and other disturbances?
First, you should recognize that we cannot monitor every voltage and current in a particular installation. Many older recorders are limited to 32 channels of information. New digital machines allow 64 channels or even more. Either way, the precise data to be monitored must be carefully selected to get the maximum amount of information after a fault has occurred. At this transmission substation, for example, some of the more important quantities to monitor are bus voltage between each phase and neutral, line current in at least one phase, line residual current, transformer neutral current, and received carrier signals for each line. Let's look at each of these quantities and see why they are important in analyzing faults. Bus voltages are important because they can usually tell us what type of fault has occurred. Low voltage on one phase indicates a single line-to-ground fault somewhere on the system. Two low voltages can mean a line-to-line or double line-to-ground fault. Three low voltages indicate a three-phase fault. We can sometimes save on channels by routing three voltages, A phase, B phase, and C phase, all to one channel. This is called multiphasing or multi-channeling of the voltages. It is done by feeding the measured three-phase voltages to a rectifier circuit. The output voltage of the rectifier consists of just the peaks of the voltages in each phase, and this is what is printed on the oscillogram. The scaling which represents voltage is different for each phase, so that we can easily differentiate. In this trace, the A phase appears to have the highest peak, followed by B, then C. As a matter of fact, this oscillogram shows the incidence of a fault. Look here, the B voltage has decreased, while A and C remain normal. Multiphasing comes in handy when we wish to monitor voltages on individual lines in addition to the bus voltage. A common arrangement would be to use a separate channel for each phase to neutral bus voltage, and then multi-phase selected line voltages. It's also important to look at phase current in each transmission line. The current traces can then be compared with voltage traces to confirm which phase or phases were faulted. A sharp rise in current and drop in voltage on A phase, for example, is a pretty sure sign of an A phase fault. Often there are not enough channels to monitor each phase current of every important line. So, quite often, only one phase of each line is monitored, with the phases alternating from one line to another. However, every major transmission line should have its residual current monitored. Where CTs are Y-connected like this, we can conveniently measure residual current or 3I0 current in the neutral return circuit. These are the same CTs that provide input to the protective relays for line protection. As you know, the residual current, IR, is the phasor sum of the three-phase currents. Normally, it is very close to zero. But when a line-to-ground fault occurs, this current becomes very large. You will often see the residual current expressed as 3I0. Remember, the magnitude of current for a single line-to-ground fault is just 3 times its zero sequence component. Another very sure way of detecting ground faults is to monitor the current in the grounded neutral of a Y-connected transformer winding. Again, this current is quite small under normal, balanced conditions, but rises significantly when a ground fault occurs. Another important quantity to measure is the carrier signal, which may either block or initiate tripping. Typically, just the received signal is monitored for each line. This signal may be generated locally or at the far end of the line. With this information, we can often spot the cause of relay and breaker misoperations during faults. Here's an example of how we can use oscillograms to quickly diagnose a fault condition. This substation has two lines connected to a common bus, and various voltage and current transformers are installed. Line 1 becomes faulted, and this starts the oscillograph recording the following traces: bus voltages in each phase, line current in each phase of line 1, the station neutral current, and received carrier signals on both line 1 and line 2. What can we immediately tell from these plots? Number 1, the fault was a single line-to-ground fault on the A phase of line 1. We know this from the depressed A phase voltage at the substation bus. The other bus voltages are normal. Also, the A phase line current undergoes a sharp rise, while the other phase currents are unaffected. Finally, the station neutral current also increases from almost nothing to a large value. This indicates a line-to-ground fault. Number 2, the fault cleared in about 4 cycles. After 4 cycles, the A phase bus voltage is back to normal, and all 3 line currents plus the neutral current go to 0. This tells us that the line has tripped out of service at both ends. Number 3, the line reclosed successfully after 20 cycles of dead time. This is obvious from the resumption of load current. Notice that the local breaker X closes first, and the remote breaker Y closes about 2 cycles later. During this period, the line is energized from one end only. The small current flowing is due to line charging. After the remote breaker closes, load current again flows. Number 4, only the faulted line has tripped. We can tell this from the received carrier signals on lines 1 and 2. Since this is a carrier blocking scheme, a received signal means that high-speed tripping is blocked. You can see that the system operated correctly. The unfaulted line 2 breaker receives a blocking signal, while the faulted line 1 breakers receive no signal. This allows line 1 breakers to trip at high speed and clear the fault.
This example has demonstrated a case where the protection system worked exactly as we expected. The role of the oscillograms was to confirm this fact.
Here's an example of how oscillograms, along with some computer simulations, can help pinpoint the location of trouble areas along a transmission line. The system one-line diagram shows 2 substations, A and B, separated by 100 miles of line. Both stations are equipped with oscillographs that monitor transformer neutral currents INA and INB. This installation suffers a particular problem. The line trips and recloses on a recurring basis. The faults seem to occur whenever the line is heavily loaded and wind velocities are above normal. This leads us to believe that the line is sagging under heavy load and making tree contact. But we have no idea where the problem is located. We can prepare for our investigation by first running a series of simulations using a short-circuit computer program. First, we assume that a fault occurs at various points along the line, say 20 miles, 40 miles, 60 miles, and 80 miles. For each different location, the computer program calculates a ratio, INA divided by the sum of INA and INB. This ratio represents the fault current contribution from station A divided by the total fault current. When the fault current ratio is plotted against fault location in miles, we get a series of points and a curve that looks like this. If the fault is very close to station A, INB will be quite small compared to INA, so the ratio will be close to 1. On the other hand, if the fault is close to station B, INA will be small and the ratio will be close to 0. For a fault near the middle of the line, INA and INB will be about the same, so our ratio is close to 1/2. Of course, we can create a whole family of curves for different system conditions, such as maximum generation and partial generation. Now that we have the simulation curve, how are the oscillograms used? Well, after a fault occurs on the line, the oscillograms are checked, and the magnitude of neutral current in each station is read from the plots. For this particular fault, INA is 1,500 amps, while INB is 4,000 amps. Our fault current ratio is 1,500 divided by 5,500. This works out to be 0.27. Now, going back to our computer simulations, we can select the curve that most closely matches system conditions at the time of the fault. The ratio of 0.27 corresponds to a line length of about 75 miles. Thus, we conclude that the trouble spot is approximately 75 miles along the line from station A to station B. In this particular case, a foot patrol located the probable tree contact within a mile of the calculated distance. The problem of recurring tripping of the line was solved by tree trimming. Incidentally, some utilities use fault locators which are programmed to perform the calculations and then give us the exact distance to the fault.
Okay, in this segment we have shown a couple of examples of how valuable oscillograms can be in a fault investigation. In the next two segments, we'll consider some actual case histories of faults and how they were investigated. At this time, switch off the videotape, study this material in your workbook.